The next slide is basically a small assignment in which we have to check whether the given numerical is satisfying the condition for applying DDM, direct design methods. So it's not a tough one, you just need to check. First one is the ratio of live and dead should be less than 2. Then for each panel the ratio of L1 square over alpha, it should lie between 0.2 and pi. So you have checked this one in this numerical. Now the main thing is to longitudinally distribute the total factored static moment m0, which we have calculated in the first step. Before this, I will just explain few things. Always remember that at the support locations, if you have some support locations, you will always have a negative moment over there. And in between the supports where there's a span or mid-span, we call it like a mid-span, you will always have the positive moments over there. The support can be in the form of like a slab can be supported by a wall. It can be either column, maybe then a beam, which is breaking the slab panels. So at these all locations, the moments will be negative over there. For example, coming towards our own numerical, the one we are just going through right now. Okay, let's look at this example. I'll just focus on this thing, the one I'm highlighting right now. So this one, this first one, it is called the exterior support. This one is called first interior support, and it has two faces. The face at this point, it is called exterior face of first interior support, and this one, it is called interior face of first interior support. What we have to do is we have calculated the total factored static moment m0. Now I will distribute this moment into 5 locations. The first location will be this one. This will be the first location. Definitely, because it is lying on location 1 is on support, it is on column, so it will be a negative moment. This will be the location 2 in between the supports. Because it is in between, that's why it will be a positive one. Location 3 will be at this point. It will be a negative moment. It is on the exterior face of first interior support. Similarly, location 4, it will also be a negative moment. And then location 5. All other in this direction, they will be repetitive of 4 and 5, 4 and 5. Again and again, they are repeating again and again. I'll just write it again here, negative, this one positive, both of these one as negative, and then this one again positive. The first 3 locations, for these we have to select a particular case. Once you have selected a particular case according to your situation, you will get coefficients for these one. For location 4 and 5, we have typical values. I'm just going to show you right now here. This is for location 4 and this is for location 5. It's always remain constant, 0.65, 0.35. Onwards, it's always again 0.65 here, then 0.35, then 0.65, then 0.35. It keeps going on the same way. So basically you have to first find a particular case, then depending upon that case, you will select 3 coefficients, 1, 2 and 3. And this will be for location 4 and this will be for location 5. This is just theory. So now these are the cases, the one I discussed with you. I'll just go through one by one. The first case is basically telling you that this is the exterior part and this is the exterior support, the one I'm highlighting right now. So it is basically showing that the exterior support is a masonry wall. Just remember that A masonry wall is not fixed with the slab, so the moment on this part is always zero. The slab is not transferring moment, it is only transferring gravity loads at the connection of slab and masonry wall. That's why the moment here is m naught is equal to 0. The coefficient taken here is 0. So once you multiply m naught with the 0, the distribution of moment at this location will be 0. So this is for first location. Now for the second location, this is the midspan. So the moment is 0.63 of m naught, because this location, this is in span and it's a positive one. That's why it is considered a positive 0.63 of m naught, where m naught is the total effective static moment, the one you have calculated in the first step for each of the 4 rigid frames, rigid frame A, B, C and D. The third moment here is 0.75 of m naught, which is at this support again. That's why it's a negative moment, because it is acting at the support, so it will be a negative moment. So 0.75 of m naught. And this is basically telling that the slab is resting directly on columns and there are no beams here. If you can see here, there are no beams. This is basically a slab which is resting on this column. So this is the first case. What's the second case is? Let's see this one. This says that this is an exterior support again, but the exterior support is having a beam here. This is a beam here at this point. Then there's a slab, and the interior support, it is also beam here. So this is basically for a slab beam system. Like there is a slab going on here. This is a slab. The slab is resting on the beams and beams are resting on columns. This one is exactly similar to the case what we are dealing right now for the conventional slab beam system using DDM. So the coefficient here are for location 1, the coefficient will be 0.16 of m naught, because this is exterior support moment, that's why it is negative. The second moment is 0.57 of m naught, which is in between span, that's why it is considered as positive. Then there is a third moment, which is again at the support, but the exterior face of first interior. This is called first interior support, and this one here at this is the exterior face. This one is called the interior face. The coefficient at this interior face, which is at location 4, it is constant 0.65 of m naught always. So the 3 coefficients are given here, first, second, and this one is the third coefficient. This particular one is the case we will use for finding the longitudinal distribution of moments, because the numerical we are given, it is exactly according to this case. Now coming toward the third case, here it says that the slab is resting directly on columns. See, this is a slab and the slab is resting directly on columns. There are no beams at the exterior periphery, there are no beams on the interior. This system is a flat plate system. So the coefficients again here are location 1, the coefficient is 0.26 of m naught. For location 2, this is the moment, 0.52 of m naught, and for location 3, 0.7 of m naught. Location 4, the moment is 0.65 of m naught, and for location 5, the moment is 0.35 of m naught. These are always same. Location 4 and location 5, these are called the typical coefficient for moments. The fourth case is showing that there is a slab system. Slab is resting on the exterior support. There are beams and the beam is resting on column, but for the interior support, the slab is resting directly on column. There are no beams here. You can see there is no beams here. So this is again a flat plate slab system with exterior beams. I already told you that flat slabs and flat plate slab systems, they don't have interior beams. You will never see interior beams here, but there is a possibility that they can have some beams running on their exterior peripheries. So this is a flat plate slab systems. The coefficients are the same. This is for location 1, location 2, location 3, and for the typical location moments, you will going to use 0.65 of m naught and 0.35 of m naught. So it's clear. This is the fourth case. The slab is resting on a rigid wall at the exterior face, and for the interior support, the slab is resting directly on columns. So the coefficients are this one. So depending upon a particular case, you will going to select coefficients for the first 3 locations, and for the fourth and fifth location, you will gonna use the typical coefficients 0.65 and 0.35 m0. These have been shown again. Just read out the theory. Now we will do a longitudinal distribution as an example here, because we have already calculated total factored static moments for rigid frame A, for rigid frame B, for rigid frame C, and for rigid frame D. All these have been calculated in our previous lecture. So now I'm just going to take one of them and do a longitudinal distribution for this one. The steps for the rest of them, it will be the same, so you can perform them. So now just focus on rigid frame A, where we have a 448 fit kip moments. This is total factored static moment for equivalent rigid frame A, which was calculated in the first step of this method. So now we will going to distribute this 448 into location 1 moment, location 2, location 3, 4 and 5. You actually have to draw a figure like this one, where you will show that these are the calculations for rigid frame A. This was location 1, so the moment is here, -72. This was location 2, and the moment is shown here. At the interior support we have two different moments, 3, and then other is a 4 here, so this is 3rd and this is 4th, and then this is the 5th one. So we already discussed 4th and 5th are the typical one, and you don't need to find this one. It will be always be a repetitive of location 4 moment. So now how we have converted 448 into 72, 255, 313 and all these moments, we're just going to look at this one, because you can see that this system is having slabs, and the slabs are resting on columns and beams. So it is a conventional slab beam system, and for this one we have particular coefficients there. Once I go in the slides, so this was the case for our numerical that I have to select these coefficients 0.16, 0.57 and 0.70 for the three locations, location 1, location 2, location 3, and for the other two location 4 and location 5, I already told you that we have typical coefficients. For location 4 it is 0.65 of m0, and for location 5 it is 0.35 of m0. So just remember these coefficients for now, and I'm going to show you 0.16, 0.57 and 0.70. So we will distribute this 448 kip moment. See, the calculations are shown here. These are the calculations for rigid frame A. For location 1, the coefficient is 0.16, the one I showed you earlier. 0.16 of this is m0, because we already said for this equivalent rigid frame A, the value of m0 is 448 kip moments. So 0.16 of m0. Then for location 2 we have the coefficient there 0.57, it is multiplied with m0 again. So these are the moments at these 5 locations. In this way you will gonna distribute the total factored static moment m0, which was 448 fit kips calculated for the equivalent rigid frame A. You will distribute this moment into 5 locations using these coefficients, the one we have discussed right now. This was location 1, then location 2, then location 3, then location 4, and this was location 5. These are the two typical one, and for this we have selected from a case. So in the same way you will gonna do the distribution for the equivalent rigid frame B, C and D. Just for your convenience, because the total factored static moment for B is half of the total factored static moment at A, so all these values, the one you have calculated right now, these will be divided by 2, so we will get moment distribution for the equivalent rigid frame B. The coefficients will remain same, but because the total factor static moment has been reduced by 2, so you're gonna get these values. Now just look at equivalent rigid frame C. So now the equivalent rigid frame C and D, they are running in this direction. along the y-axis. So this is basically the exterior support is here. This is the exterior support. So you are going to see the moment here 1, then this is the location for moment 2, then there will be a moment 3 here, and then a 4 here, and then a 5 here. So this will be a distribution of moments. Again, these 3, 1, 2 and 3 will be calculated using case, and 4 and 5 are the typical one. The coefficients are same, because for location 1 we have the coefficient 0.16. You're just going to multiply it 349, which is total factored static moment calculated for the equivalent rigid frame C. So 0.16 multiplied by 349, the coefficients are the same, there's no difference, but because the total factored static moment is different from the previous case, shows you will end up with the different values. In the same way, you can do it for the rigid frame D.